A machine fills packets with sweets, and 1/7 of the packets also contain a prize. The packets of sweets are placed in boxes before being delivered to shops. There are 40 packets of sweets in each box. The random variable t represents the number of packets of sweets that contain a prize in each box. And essentially, we've got a binomial distribution. We're asked to state a condition for t to be modeled by that. So there's four conditions to be aware of. There's a fixed number of trials, but it's kind of, that's not really, I mean, that is a condition, but it's kind of, we know that it's valid here. There's either success or failure, but that's kind of clear as well. So I would go with one of the other two, independent events or fixed probability. But just make sure you give context, because it does say state condition needed for T to be modeled by B. So I said the sweet packets must be picked independently, independent of one another. Here's the mark scheme. Okay, it does say context, independence, or random packing. Prizes must be placed in packets at random or independently of each other, or about constant probability. The probability of a packet containing a prize is constant, the same, fixed. So that's what you need to go with. Right, now we're asked to find the probability that the box has exactly 6 packets containing a prize when we pick one. So that is the probability that x equals 6. We can just put this in our calculator, although I will talk about what the calculator is actually doing in a minute, because it's important to understand it. So distribution, binomial PD, because it's just an equals, just a variable, 6, 40, and 1 over 7. This gives 0.17273, which I'll round to 3 significant figures, 0.173. If you're doing it, from first principles, then it would be we are arranging 40 objects. So there's 40 factorial ways of doing that. 6 of them are the same, so we need to divide by that. And then the other 34 that don't have a prize are the same. That's your 40C6. And then we just look at the probability of getting 6 successes in a row. So that would be 1 over 7 to the 6. And then it'd be 34 failures in a row. So 6 over 7 to the 34. And if you work that on your calculator, you get exactly the same answer. So it's, just getting 6 successes, 6 failures, sorry, 34 failures, but then all the different ways you can arrange that. That's how it works. Now we want the probability that the box has fewer than 3 packets containing a prize. Fewer than 3. Don't be caught out by this. This is actually going to be less than or equal to 2. It can't actually equal 3. So for this, you could add up 0, 1, and 2, but best to use binomial CD. So it even keeps it here. So we've got just 2 now and keep everything else the same. 0.061587. Which is then 0.0616. Okay. We're told that Camille's sweet shop buys 5 boxes of these sweets. Find the probability that exactly 2 of these 5 boxes have fewer than 3 packets containing a prize. This is actually another binomial distribution. So I'm going to call it X. X follows a binomial distribution. We've now got 5 trials. We're trying 5 boxes out. And with each box, we want to know the probability of getting fewer than 3. Well, that's actually what we found out in the previous part. It's 0.06. Now, when I did it, and I would advise this, use the full version, okay, just to avoid any rounding errors. I think you get away with it if you do, but best to be safe and precise. So now we want the probability that x is equal to 2. And we've just got a different distribution, but it's the same idea as the first part. So, all right, I need to go back to binomial PD. Now x is 2, n is 5, probability is 0.061587, which gives us 0.03134. Or 0.0313. Finally, Camille claims that the proportion of packets containing a prize is actually less than 1/7. A random sample of 110 packets is taken, and 9 packets contain a prize, which is below 1/7, but we need to see if it's statistically significant. So we're going to use our hypothesis test to test this claim. State our hypotheses clearly and use a 5% significance level. So H naught is going to be that P is equal to 1/7. We should define this. You know what? In the past, I've not always done this, but it's best to do so. Probability that a random pack contains a prize. So that's our go-to. That's going to allow us to do some calculations. But then H1, our alternative hypothesis, is that in fact P is less than 1/7. So I'm going to assume H naught is true. And then define, I'm not going to use X. I already used X, so that you could if you wanted, but Y is going to follow a binomial distribution with 110 trials now, probability success 1/7. Let me define Y as well. Y equals the number of packets containing a prize. Out of the 110 we're selecting, but that's kind of implied. So now I'm going to work out the probability that Y is, we know 9 packets, so I'm going to find the probability that Y is less than or equal to 9. Right, this equals, let's go back to distribution, back to binomial CD. We've got now less than or equal to 9, 110 trials. Probability is 1/7. And we get 0.03829. So this is a very small probability. It's actually below our threshold. That's what the 5% represents. And it means we're going to reject H naught. We're in the critical region. So reject H naught, sufficient, then just give an answer with context, sufficient evidence to suggest proportion is less than 1/7, at least at the 5% level.